Okay, so hey everyone, it's Presley of ActOutGames.com here for a magnet explanation vlog. We're going to explain the magnet thingy.
So now
We've got our own strongy magnet.
now that we've looked at our magnets and what they can do yesterday, let's talk a little bit about why they do it.
Yes. I get this magnet's attaching to everything.
Let's put it down. So, what makes a permanent magnet? What'd you learn?
So, just start. So, it has to have half full atoms.
Yeah, half full electron shells.
Electron shells.
Yeah, why is that?
Well, at least valence shells.
Yeah.
Valence shells.
Doesn't really matter so much what shell it is, but yeah.
So
it needs a
half.
Yeah, the middle like half full shells. Yeah, why does that matter?
So they can't pair up and cancel each other out.
That's right. That's exactly right. So, if you looked at our blogs on shells and orbitals and how electrons form around atoms, then you'll know that the electrons fill up in a certain order when they fill up an electron shell. SPDIF, that's right. So it's SPDF, and it can be any of those. Well, really, the S doesn't matter because there's only 2 electrons in there, so it can be by itself, but it's not a big deal. It's not strong enough. It's not strong enough, right? Yeah, that's right. So what happens is in the orbitals, there are 2 electrons in each orbital when it's full. Okay, so the S just has 1 orbital, and that'll hold 2. And when there's 1 in it, it is basically a tiny little magnet. An electron can be a tiny little magnet. It's spinning, and it's basically like an electrical current, which is creating a magnetic field. And when the other one comes into that same shell, it spins in the opposite direction and cancels out the first one. So when there's 2 electrons in one orbital, it cancels that out, right? But
it can't be like magnetic.
Then the atom wouldn't be magnetic. So it doesn't. It's harder. They don't like to be in the same shell with each other. Or the same orbital with each other, sorry. So if there's a free orbital for them to go into, they go into that first, right? So in S, the first one goes into S, and then the second one goes into S with it, because there's nowhere else to go. But in P, for example, there's 3 orbitals, and so it goes 1, 2, 3. 1 in each, and then goes back and fills them back up. So, like you said, when it's half full and there's just 1 to 3 that are by themselves, they don't have another electron in there to cancel them out. And so the ones in there that aren't canceled out, they make a magnetic force in that electron. So we drew a little picture, and very much like the minute physics kind of thing. So you can look and see at the top of the picture, it shows that there are 2 electrons sitting next to each other, and the magnetic charges are reversed. They cancel each other out. But then the 3 electrons around the outside don't have a pair electron with them. And so overall, they're creating a magnetic charge for that atom. So that atom is a tiny, tiny little magnet. Okay, absolutely right. That's the first thing that has to happen. What's the second thing?
The atoms in a small group of atoms, well, not a small, a really large group of atoms, they all have to be facing the same way. Yeah,
so there's the way that atoms form when they come together. So if you take a piece of material, that there's 3 different ways that the atoms can group together. They can either group together facing all the same way, which makes a magnet. Makes a strong magnet if they're all facing the same way, because all of their north poles are lined up and all their south poles are lined up, right? So that makes a strong magnet. Another way that they can line up is that that's right, they line up in opposite. So 1 up, 1 down, 1 up, 1 down, 1 up, 1 down. There's more pictures of these. Hopefully I'm probably showing those right now. But they show, when that happens, they cancel each other out again. So the atom, the electrons don't cancel each other out. But when the atoms come together and you've got more than 1 atom, they cancel each other out because they flip. So that's another opportunity for it to not be magnetic.
What's it called? This kind of.
And then sometimes they can just be random. And when they're just random, then they're not lined up enough to be magnetic, but you can still attract a magnet to it.
When you're on the screwdriver, it's how that becomes a magnet. Because it has these other kingdoms.
That's next. Yeah, that's the next thing. The next thing is domains, right? So if
they all have to be aligned.
Even if you have the atoms, where when the atoms come together, they line up and they face the same direction, then a lot of times that happens in little groups. So here's another picture on the whiteboard. There's a big chunk of material, and it's broken up into little things called domains. And within each domain, all of the atoms are facing the same direction, and so the magnetic charge is facing the same direction, but the domains all kind of face in random directions. And so, again, they kind of cancel each other out, right? So if in the material you've got a bunch of little domains, even if each of the domains is lined up, then if the domains are sort of scattered, then they can totally cancel each other out. And so that's what the screwdriver is like. So it has...
And then you can rub the magnet on it, making them all face the same direction.
That's right. So when you rub the magnet on the screwdriver, it makes all of those domains in the screwdriver that are all kind of wonky and pointing different directions snap around and point in the same direction, and suddenly you've turned the screwdriver into a magnet. That's exactly right. So all three of those things have to happen. You have to have electrons that aren't paired and cancel out at the atomic level in the individual atom. And then the atoms, when they sit next to each other, have to be aligned so that their north and south poles are facing the same direction. And then the little domains of groups of atoms all have to be aligned in the same direction to make a big piece of material be a magnet. That's why magnets are so rare, because all of those things have to happen.
By the way... we got all this from Derek again, so thanks, Derek.
Yeah, we'll put a link down there to Derek and to Minute Physics.
Yes.
We'll put a link to the two primary videos that we watched that help this out. That'll help you understand it a lot better than we're explaining it as well. Yeah, and so the other thing that has to happen is that a lot of things that are magnetic, that have those properties, those three properties, the atoms are magnetic, groups of atoms, or the domains are magnetic, and then all of the domains point in the same direction to make a magnet. They only do that at certain temperatures. If they get too hot, then those things dissipate, and you don't have your domains pointing in the same direction. And so there are a lot of things that are magnets that are really good magnets, in fact, but they're not magnets at room temperature. So that's why you see iron.
It's this thing, but it's mixed with iron to make it strong, like a really strong magnet.
Yeah, so what they've discovered relatively recently is that you can take one of those materials that's a really strong magnet that's not magnetic at room temperature, and you can mix it with other metals. And what do you call that when you mix metals together? Do you remember?
Chemistry.
Chemistry. An alloy. So you can make an alloy, and that alloy will maintain its magnetic properties at room temperature. And so that's these like rare earth magnets that are super strong magnets. That's where those come from. Is that
they're really strong.
They're things that would normally be magnetic at room temperature, but because they've made an alloy and mixed them together, then they maintain their magnetic properties. Cool. So that's how a magnet works. There's the three different things that have to happen, and why what we learned about the way that electron shells form is important to understand how a magnet works. I know, we're not done yet. And then that's also why when you rub the magnet on the screwdriver became magnetic, because it aligned those domains. And what's the one more thing?
This!
The electromagnet.
Yes, it's beautiful.
So this is much more complicated here. You can pick that up with it.
It's just a reminder, like, it's a little bit hot after.
It does get a little hot after a second.
Did I do it right? No, I didn't.
You see it. So you want to talk to us a little bit about how the electromagnet works?
It works something relativity.
Special relativity.
Special relativity.
Yeah, I don't have a paper clip to pick up. It's probably only strong enough to do that. Yeah. Okay, go ahead.
You can go on.
Do you want to talk about special relativity?
Special relativity.
There we go.
Special relativity is basically that something that's moving is only a little bit smaller than something that's staying still.
Yep.
So that's how this electromagnet works. So say not the hydrogens.
Electrons and protons.
The electrons. Say the electrons are moving in this direction, and they shrink a little bit.
The protons are the ones that, there's a special case with electrons that they don't actually compress.
Yeah.
But the protons, who are moving relative to the electrons. So when there's electric current flowing through a wire, you got a lot of protons and you got a lot of electrons. And the electrons are moving and flowing through the wire. but this is why it's relativity. Relative to the electrons, the protons are moving. And like you said,
point of view.
From the electron's point of view, that's exactly right. So protons, like you said, special relativity, part of what it says is that when something is in motion, it actually shrinks a little bit.
Only a little bit.
Well, it depends on how fast it's going. But for the speeds that we're talking about, it's tiny, tiny, tiny pieces. But these things are so tiny and the charges are so strong that tiny bit of special relativity and the tiny amount. So when you're looking at a wire and nothing's moving in the wire, the protons and electrons balance each other out.
Like right now, there's nothing in it.
That's right. When there's not plugged in, the positive charges and the negative charges cancel each other out. Right? They're balanced, like we were talking about with the other things in the atoms. But when the protons start moving relative to the electrons, special relativity says that the space between them compresses a tiny bit. Tiny bit. But it's enough that it takes that balance away. And so now you're no longer canceling each other out, and there's an electric charge that takes place. So the positive becomes weaker and the negative becomes stronger, right? Or the vice versa. The positive becomes, yeah, that's right. The negative becomes stronger, the positive becomes weaker. And that makes an electronic force, an electronic field. An electric field is basically a magnetic field. So that's why when there's current flowing through a wire, special relativity screws with the balance of electric charges between the protons and the electrons, and that makes a magnetic field around the wire that's flowing. Which is crazy, right? I mean, it's just absurd.
And so why it happened? Nobody knows.
Yeah, watch Derek's video, because he shows a really great visualization of how it works, and there's a couple of good Wikipedia articles that explain why the electrons don't compress, which is it's a whole different thing. Wikipedia's got some good stuff too, right? Why the electrons don't compress when the protons do compress. That's kind of a different thing, but it's one thing that sort of shows special relativity in action, right? It's an
everyday thing.
An everyday thing, a magnet, right? It's hard to believe that a magnet, and looking into a magnet and how it works,
is very complicated.
It's very complicated, but it goes to the things that we learned about how electrons fit into shells, and the charges of electrons, and how they pair up and or not don't pair up, and electric spin and canceling each other out. So it's a lot of atomic physics go into how this thing works, and then also special relativity dealing with an electromagnet is a really amazing thing. It's an example of how special relativity it shows up in everyday life, right? It's proof that something moving shrinks. Which is crazy.
Yes.
Right? What else happens in special relativity aside from it shrinking? What happens?
I don't know. It shrinks.
It shrinks?
And it can.
And what's the other thing that we talked about?
Travel.
What makes it be able to kind of time travel? What happens?
It is so if you're moving fast enough. Other things. Your clock goes slower. Time
goes slower for the thing that's in. So when you're moving,
you can time travel by 0.00000
tiny amounts, depending on how fast you're going, right? But like when something is in motion, the same special relativity says that when something is in motion, time passes more slowly for that thing too, right? So if you're moving faster than someone else, time is passing more slowly for you in tiny amounts at speeds that we're talking about. But as you approach light speed, it becomes a significant change, right? And that's why
but then you can time travel.
Certain types of time travel are theoretically possible, because as you approach light speed, those differences become greater and time passing more slowly for you. So if maybe it's 10 years pass for you, but 100 years pass outside, away from you, for somebody else. And when you stop moving, now you're 10 years older, but everybody else is 100 years older because that special relativity. Ridiculous stuff, right? Crazy stuff. And not stuff that you would think you would get into by looking at a magnet and how a magnet works. But that's how it works. Anything else you want to add about the magnet study?
Well, not about the magnet study, but happy almost New Year's.
Happy almost New Year's. We're posting this on New Year's Eve. We're shooting our New Year's thing today. We'll post that tomorrow. But yeah, absolutely happy New Year's, everybody.
Yes.
Learn about magnets. It's super cool, right? It's one of the coolest things that we've looked into, isn't it?
And you can make dinosaurs with them.
You can make dinosaurs. Do you agree? It's one of the coolest things that we've looked into. Cool. It's pretty neat. It's it makes your head spin. Yeah. Remember you told me that it made your head hurt.
I had a headache.
It gave you a headache looking into magnets.
information.
Too much info, right? But super cool, right? I love it. We'll keep digging into magnets a little bit because they tie into all of our atomic quantum physics, right?
Great.
Cool. All right. Bye. Happy New Year.